Hello, everybody. Today we're going to be exploring the electrode interface and how electrode interfaces behave during electrochemical reactions because the electrode interface is actually where the most significant parts of the electrochemical reaction take place. And to do this, we're going to dive straight into an example of an electrochemical system to explore and to understand. And today we're going to be looking at the electrodeposition of copper, right? This can be modeled by the equation Cu2 plus 2 electrons reduces into copper solid. This this reaction takes place at a voltage of 0.34 volts versus a standard hydrogen electrode. Now what this means, this part right here, basically every single electrochemical reaction occurs, well, its equilibrium occurs at a specific voltage. Uh, and the way the voltage works, you can never say that something, you always have to compare voltage to another potential or voltage. So in the same way that, like, for example, a mountain is only as tall compared to, say, ground the ground. And similarly, potentials, you have to always compare them to some other potential of another electrode. So in electrochemistry, we always compare voltages of an electrode with some kind of standard electrode. So in this case, most modern electrochemistry uses the standard hydrogen electrode, but there's also like the calomel electrode, which is a mercury electrode that's commonly used as a standard. But that what that means is we set the standard hydrogen electrode to 0 volts, and then anytime we look at a chemical reaction, we just compare it to it. So in this case, the voltage of required to drive this electrochemical reaction is 0.34 volts. Now, let's say this occurs on some platinum electrodes, right? This deposition will do on 2 platinum electrodes. And the reason that platinum is often used as an electrode is because it's very inert, very non-reactive, so it doesn't cause any other side reactions than what we want to occur, which is good. And then also, platinum is very, uh, very conductive, so it doesn't add much resistance to the system, which also helps us preserve these ideal qualities that we want. So we have these platinum electrode and they're connected to a voltage source. And this voltage source drives current. And in the solution, the electrolytic solution, we have our copper ions. And let's say it's copper ions and there's sulfate ions as well, right? So we basically just mixed a copper sulfate solution. Let's set it at 1 molar, which is much more saturated than we need for electrodeposition to definitely occur. And that way these copper ions will reduce onto the platinum electrode. Well, hopefully, will reduce onto the platinum electrode to form solid copper. Now, let's say we set up this experiment and we run voltage at an overpotential of around 0.6 volts, so a potential of 0.9 volts, driving current in this direction since we need this to have the electrons so that the copper can bond with the copper ions can bond with the electrons to form solid copper, making this electrode the cathode and this electrode the anode. And let's say we run this reaction, what happens? Well, I've done this exact experiment before, and I can actually share the results that you would actually see. This is real data that I collected after running this experiment. And actually, I'll show you this and I'll show you an image as well. This here are some, 1 second. Yes, okay, perfect. So yeah. These right here are some images of platinum electrodes that we actually coated in copper, and you can see it there. Um, yeah, and then this is the actual data that we recorded of current over time. You can see voltage is at a constant zero point 0.9 volts, and the current does some interesting things that we want to be able to describe the phenomenon of. Just kind of observing what's going on in this data, we can see there's this initial spike in current, and actually the current goes higher than this. It's just cut off, but notice this initial spike in current followed by quickly declining, rapidly declining to a minimum, and then kind of slowly increasing at like a steady state sort of increase, right? Which is occurring at around 3 microamps. Now, we want to be able to explain what is going on and why do we see these different weird results, right? So the way to do this is actually to just think about our electrochemical system as a as an electrical circuit, right? If we were to draw our electrochemical system as a circuit, well, we have a voltage. The way you would actually describe it, the best way to think about it as is a voltage connected to a resistance and then connected to another resistance, which is in parallel, oops, which is in parallel with a capacitor, and this is connected back to voltage. So let's try to explain what each of these components represent are theoretically. First, this first resistor is the resistance of the system, and this is just stuff like the wires, which will have some resistance, the solution itself, which will have some resistance. Even the electrodes, even though we're using platinum electrodes, they still have some resistance. So those have to be included as well. And all those resistances summed up create the resistance system that contributes to this like deal, non-ideal reaction. And then there's this other resistance right here. This resistor is to represent the resistance of the mass transport combined with the resistance of the electron transport. So what this basically means is for our electrochemical reaction to take place, it takes time and it takes work for the electrons and the ions to move to the electrode, right? Because our chemistry has to occur at the electrode. We need these electrons to move from inside the electrode to out, and we need these copper ions to move from the bulk solution sorry, to the interface of the electrode. And that takes time and that takes diffusion. And that diffusion takes time, which limits the speed of the reaction and the current and the amount that can be deposited. So, and another thing, as you could expect, the mass transfer tends to be a lot bigger than the resistance of the electron transfer, depending on what system you're working with. Our In our case, it's likely that the mass transport is the limiting factor, but there are situations where the electron transfer can be of greater resistance. But in our situation, yes, the resistance of the mass transfer will be much greater than the resistance of the electron transfer. And that makes intuitive sense. Just electrons are probably going to move faster and to the electrode interface than the copper ions. So that explains this resistance. But why is it in parallel with a capacitor? Well, to understand that, we need to think atomically about what is going on with our electrode, right? So let's draw out, this is one electrode, right? And our electrode is, at least the cathode, is negatively charged because there's electrons going to it. This will cause positive ions to come really close to it. In this case, the copper ions to come very close to it. And in fact, we'll actually see this gradient of positive ions occurring all throughout very close to the electrode until we get to the bulk solution where it goes back to being just to being a pretty even mix of the minus and the plus ions. But before that, there's this, what we call diffusion layer, where diffusion takes over and the ions transport themselves to the electrode because they can see the negative electrode and, oh, sorry, and they are attracted to it. In fact, some more terminology. We have the inner Helmholtz layer, which is where uh, this diffusion layer starts, and we have the outer layer, outer Helmholtz layer, where the diffusion layer ends and where the positive electrons are no longer able to quote unquote see the negatively charged electrode anymore. And same this thing that's going on here can actually just be thought about as occurring on the sorry, can be thought about as occurring on the opposite side where we have an anode, a positive electrode with negative ions, maybe the sulfate ions, attracting to it. Now, if you know anything about how a capacitor works, basically what a capacitor is two metal plates that are separated apart. And so when you have a voltage, this side of the plate becomes very positively charged if, for example, the current is going this direction, and this side becomes negatively charged. And that creates an electric field in this space, which is the capacitor. And so you can see that exact capacitor forming here with a negative electrode, which is a negative platinum metal plate, and a positive platinum negative plate. And in between, an electric field forming, which we see in the form of this diffusion layer, and the diffusion layer on the other side, on the anode side. And if you know anything about and so that explains what this capacitor is doing here. It's called the double layer capacitor. Now, if you know anything about how capacitors work, you know that it takes that when a capacitor first charges up, so before a capa when a capacitor before a capacitor gets attached to a voltage, it's neutral. But it takes a small amount of time for the capacitor to charge up and reach this and create this electric field. And when it does, during that instant, there's very little resistance, and so current is able to flow through the circuit and at a very low resistance. And so that's what this spike we see here is. It's actually, if you've done like the differential equations for capacitors before, you'll know that I is proportional to E minus T over tau, where tau is like the time constant, but you know that there's this exponential decay when the current charges up. It spikes and then the current declines really rapidly until it reaches this minimum, which is probably where this capacitor completely charges up, which means that now all the current is flowing directly into this other resistor we have, right? Which is causing this, and that resistor is a lot greater in resistance than the capacitor, which is why the current is so much less, because V equals IR, so R is inversely proportional to I. So that explains this initial spike. And this initial spike we call a non-faradic current. And I'll explain why in a minute once you see what a Faradaic current looks like. And actually, wait one second. Now, the other thing that's kind of difficult to explain is then why does it increase? Shouldn't it just stay at that resistance? Is the resistance of the system or the mass transfer, the electron transfer changing? And the answer is that Yes, it actually is. It is changing. What's happening is that okay, what's happening is that second, as our electrode acquires this copper solid, this thin film that we see over here, its surface area is increasing. Uh, how does that work? Well, just um, let's think about it atomically. We have this perfectly flat platinum electrode, and then suddenly little bits of copper start to form onto it. These increase the roughness of the electrode, which increases its surface area. And now that there's way more surface area, there's way more uh, area for the reaction to take place, which reduces the resistance of the electron transfer as well as the mass transfer. And when you reduce the resistance, you're able to increase the current. And so as more metal gets deposited, that increases the surface area, right? And that increase in surface area leads to a decrease in resistance, which therefore leads to an increase in current. And that's how we can explain this second half of the graph. And that kind of current is actually called a Faradaic current. So what is the difference between a Faradaic current and a non-Faradaic current? Faradaic currents are any current caused by electron transfer, right? So here, the act of the electron transferring to create copper solid is causing the current that's occurring here. So we call that a Faradaic current. A non-Faradaic current, as you might expect, is just current not caused by electron transfer. So this initial spike in current was not caused by electron transfer or the reaction or anything. It's caused by this like weird capacitor double layer. It's something completely different. And so we call that a non-Faradaic current. Now, I hope this video explained all the different things that are going on at the electrode interface. You can see a whole capacitor forms. You can understand the electrical circuit of it. And I hope that helped make understood what exactly goes on at the interface of an electrode and how it's significant towards an overall electrochemical reaction. Thank you for watching, and if you have any questions, let me know in the comments.